Good morning, guys. This morning we are going to be looking at integration by parts together. This is a technique that adds on to integration by substitution, as well as the algebraic methods we've developed in the past. First and foremost, we should always ask ourselves, why would I want to use integration by parts? You will only consider this method if you have first looked at the possibility of using either a basic integral, or if you've tried a substitution and it's failed, and of course maybe just algebraic methods could have led you to decide that integration by parts is what you want to do. Now, integration by parts requires that we have a product of functions, or is usually characterized by a product of functions, which involves usually trigonometric or exponential functions that combine with polynomials. Here are two examples of that. In the first, we have a second degree polynomial with an exponential, and in the second we have a linear function and a trig function. It might be a combination of inverse trig or logarithmic functions as well as polynomials. So in the first we have root of x, which is actually called an algebraic function with a logarithm, and we have another polynomial, so a quadratic in this case, with an arctan function. Or we have combinations of trigs and exponentials, so for instance an exponential function with a cosine, or even two trig functions but with different angles. So how does this work? Well, integration by parts could be thought of as the product rule backwards. So here is what the product rule would have taught you in Cal 1, which is that the derivative of f times g can be replaced by f prime g plus fg prime. Because the two sides of this equality are the same, then doing the same operation to both sides maintains their equality, and I'm going to choose to integrate both sides with respect to x. So notice I've just applied the integral to all terms, and because of our addition rule, I am integrating the right-hand side as individual terms. Now on the left, some of you will have noticed that we are integrating a derivative. So those are opposite operations and therefore just cancel off. And basically, integration by parts is obtained by moving one of those two terms on the right and joining it to the left-hand side. The choice I'm making is I'm going to make f prime g move to the left and add on or be subtracted from f times g. And here it is. This is actually the integration by parts formula, which I'll show you in a different format. Here I've isolated f and g prime on the left-hand side, and our integration by parts tells us we can replace this integral by f times g, so a term that doesn't require any more integration, and the integral of f prime times g. Now what we're hoping for is that the integral of f prime g will be simpler to solve than what we started off with f times g prime. Okay, so that's great, but how do we decide who f and who g prime will be? Because ultimately that's the decision we will have to make. So let's try something, and we're going to go a little bit with our intuition here at first. So here's me guiding you to hopefully not off the ledge. Here we go. Here is an integral that involves two different kinds of functions. We have on the one hand a polynomial, 2x plus 1, and e to the x, an exponential, and you can try substitution or expanding, but you'll notice that you will encounter problems along the way regardless. Integration by parts tells us that an integral f times g prime can be replaced into f times g minus the integral of f prime g. So in the integral we're trying to solve, 2x plus 1 e to the x dx, we're going to think of 2x plus 1 as the f, and we're going to think of e to the x as g prime. So that corresponds to the left-hand side, so this term right here, of our expression. And if we're going to use integration by parts, then we're going to have to figure out who fg, f prime g are in order to complete the right-hand side of the equation. So if f is 2x plus 1, f prime is 2, and if g prime is e to the x, then its antiderivative just remains e to the x. And now what you could do is just fill in the blanks. So go back to the integration by parts formula and just cut and paste the results, the f's and the g primes that you've just found. So here we go. So the two sides of this equality are equal. On the left we have the original integral we were trying to solve for, and on the right we have what it has decomposed into, or what it can be replaced by. And this is where you see how useful integration by parts is, because on the right hand side the integral you have is actually quite basic. I'm going to extract the 2 because it's a constant multiplier, and integrating e to the x is a basic rule. Okay, so I've completed the anti-differentiation process and I've added an arbitrary constant. Let's look at a different situation. So here we have 2x plus 1, the same polynomial we had a second ago, and ln of x, so a logarithmic function. This is still a combination that fits into what we described as being potentially applicable to integration by parts. And once again, we're going to take a bit of a leap of faith, because we have to decide who within this integral will play the role of f and who will play the role of g prime. So let's say we did as we did earlier, which is to pick f as being 2x plus 1 and ln of x as being g prime. Then that would mean that we would have to find f prime and g in order to complete the right-hand side of the integration by parts formula. Well, it's fine when it comes to finding f prime, because differentiating 2x plus 1 is just 2. But when it comes to ln of x is not one of our basic functions, and we have no direct antiderivative for it. So we're kind of stuck. What if we had made the other choice? So what if we had picked ln of x as f? Then its derivative is much more straightforward, 1 over x. And by choosing g prime as 2x plus 1, actually I say choosing, but we have no choice, because f and g prime together must complete whatever function we were trying to integrate. Well, from that g prime, anti-differentiating to get g simply requires we use the power rule. So I've integrated 2x plus 1 as x squared plus x. So again, back to our integration by parts formula. Here are the choices we've made. I've reordered the terms a little bit so that you can see the associations. So f is ln of x and g prime is 2x plus 1. That's the choices we've made in our second attempt. And on the right hand side are what these terms have converted into when applied to the integration by parts formula. So f and g is now x squared plus x minus, and we have a new integral, which is now the combination of f prime with g, 1 over x times x squared plus x. This integral is not direct, but actually now we can use algebraic methods such as just expansion. And I've expanded the 1 over x to the two terms x squared plus x. And once again, what we obtain is an integral that is basic, or actually whose two individual terms are basic, and we can then integrate x and 1 individually. Notice how I've added a constant to be completely general about the antiderivatives, and I also have parentheses because we are actually subtracting the entire result of the previous integral, and finally you could distribute the signs if you wanted. So how do we choose f and g prime? We probably don't want to guess every single time who should be the f and who should be the g prime. So just to structure your thoughts a little bit, you can use the following list of priorities to attribute f to one of the functions. So you will choose f to be an inverse trig functions or a logarithmic function as soon as you see one. These are the priority functions in becoming f. If there are no trigs, if there are no inverse trigs or logarithms, then you would look for polynomials or algebraic functions. And finally, if there are no inverse trigs, logarithms, or polynomials, then pick whatever trigonometric or exponential function there is. So in our examples, the first one we were looking at involved a polynomial and an exponential. Polynomials always have priority when it comes to being attributed the label f, and in this case e to the x would have to be g prime. However, in our second example, logarithms have priorities over polynomials, and therefore for that particular example, ln of x would play the role of f. 2x plus 1 would play the role of g prime. And there you go. You have a starting point with which to work with the integration by parts formula.